The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get started. On Thursday, we are really privileged to have John Bentley, who is one of the masters of performance engineering, come and give us a guest lecture. In 1982, he wrote this wonderful little book from which we adapted the Bentley rules that you folks have seen. And he's also famous for things like KD trees. Who's seen KD trees? Yeah, so he invented KD trees, and who's ever used the master method of recurrent solving? He invented the master method of recurrent solving. And so, I mean, he's just a wonderful, wonderful fellow with lots and lots of insights and just like a superior performance engineer. And he's going to talk, give a guest lecture on Thursday. And so I would encourage you to bring friends maybe who dropped the class, okay? Because this is the and others who you know, if any of you have UROPs, other people in your research group, whether they're graduate students or whatever, they're all welcome to come, because this is really, you know, one of the opportunities you get to actually meet one of the, you know, legends of the field, if you will, and you know, have a and you'll see he's very approachable. He's very approachable. So anyway, my advertisement for John Bentley. Good. So let's start. I want to talk about speculative parallelism for a little bit, because that's kind of what you need to make the code go fast. So if you look at code like alpha beta, it turns out that it's inherently serial. Okay? That is, if you don't you know, if you try to do things in parallel, then you miss the cutoffs. And if you miss the cutoffs, you know, the beta cutoffs, then you start doing work that you wouldn't necessarily need to do. And so the only way to sort of make this type of code run fast is to use speculation, which is to say that you're going to guess that you can do stuff in parallel and it'll be worthwhile, and then occasionally you're going to be wrong. But the trick is, well, how do you minimize the wasted effort when things go wrong? So let's just take a look at a very simple example of speculative parallelism, which is thresholding a sum. So here we have a little program that is returning a Boolean. It takes as input an array of size n. So thresholding a sum. So we have an array A of length n and a limit, and these are all unsigned integers, say. And I start out the sum at 0, and what I'm going to do is add up all the elements of the array, and if it exceeds the limit, then I'm going to return, okay? And so how might I optimize this code a little bit? Yeah.
Split up. You have like 4 processors. You would split up your array into 4.
No, let's say on one processor. On one processor, what might you do?
In the middle of the loop, you can check every time if you exceed it.
Yeah, once you check, so that once you exceed it, why keep adding the other numbers? Okay? So here's a code that does that. Quit early if the partial product ever exceeds the threshold. This isn't necessarily an optimization, because notice that now in the optimization, not only do I have, you know, a memory reference and an addition, I also now have a, you know, I also have a unpredictable branch. Actually, it's predictable branch. Predictable branch, but still one more step, because it's always going to predict that it's not exceeding until it actually does exceed. So that'll be pretty predictable. And, but still, I've added something into the loop, so that may be slower. How might I mitigate that problem? So I don't want to add too much into the inner loop. Yeah?
Yeah, the inner loop that goes up adds K of them and it checks.
Yeah, so basically I can do what's called strip mining. I replace the loop of n iterations with a loop of, let's say, n over 4 iterations, with an inner loop of 4 iterations, and every 4th iteration I check to see whether or not I've exceeded. Okay, so that the cost of the check is going to be, relatively small at that point. Okay, so there are ways of making this sort of go fast. Okay, so now we want to make this operate in parallel. Okay, and the problem when I operate in parallel is that as I'm adding stuff up, I want to do it. So I'm going to do this here with a reducer. And so basically I'm going to add up the values in the reducer, but now I'd like to do the same thing of being able to quit early. And so the question is, well, how can we parallelize a short-circuited loop? Okay? How can we... And so the way I'm going to do this, and this is sort of by hand here, but it's going to give you... So actually, as you know, underneath the loop is really a divide and conquer loop. And so, I could write it as a parallel loop. And now it becomes, I think, a little bit clearer how I could... in this case, what I'm going to do is return the value of the sum. And now the question is, well, how can I quit early and save the work if I exceed the threshold? Okay. Understanding that, when I'm executing this in something like Silk, it's going to tend to, go down one path, and often it's going to be a serial execution. So I'd like if it's possible. So here's one way of doing it, which is that I add an abort flag to the code, and which is going to say whether I should keep going or whether I've actually exceeded at that point. And so I'm going to use that recursively. And now I take a look at, for each time through the loop, or through the divide and conquer, I look to see whether the sum is greater than a limit, and I haven't, already aborted the flag, then I set the abort flag to be true. Okay? Why do I bother testing the abort flag before I set it to true? So notice that setting the abort flag is a race, isn't it? A determinacy race. Okay? Because I have, great, thank you. It's because I have the stuff operating in parallel is all trying to set the abort flag whenever something aborts. I can have two guys who are in parallel setting the abort flag. But if they're setting it to the same value. So it's a benign race, okay? Assuming your memory model is such that you can actually set the values. So what happens here when, why do I bother checking this? So what happens when several guys in parallel want to write to the same variable? This is quiz 1 stuff. Yeah. Yeah, you can have it bouncing along the cache. It will serialize it, right? Because if they're all trying to write, then they have to get exclusive access for it to write and modify it. And so that happens boom, 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 one at a time. And so by checking it first, it can be in a shared state, and then only one guy clobbers it, and then it'll update all the other ones. So it makes it so we don't continually have a true sharing race. And then in the checking to see if it exceeds, we basically just check to see if we basically call this function, we set the abort flag to false, and then we return the sum of all the values, and if it aborts, then it just returns early. Okay, so it doesn't have to keep going through the computation. And of course, once again, you can coarsen the leaves and so forth. So, so this is non-deterministic code, right, which we should never write unless we have to, okay, because that's the only way of getting performance. And you have to make sure, of course, you reset the abort flag after the use. And then, actually, do you need a memory fence here on the abort flag? Do you need to set, where would you put an abort flag to make sure that the value was? Yeah.
Maybe you can do it by setting it to volatile.
Yeah, so what would you have to do?
Put a
Okay, so so indeed, it turns out you don't need a memory fence here, and the reason is because the code is correct, whether it's the initial value false or whether it's become true. So it doesn't matter when it becomes true, and so there's an issue of if you put in the fence, then you know that it becomes true earlier. Okay, rather than waiting for the commutation. But that may actually slow things down because memory fences are expensive. But because the transition is always from false to true during the execution, you don't actually need a memory fence there, okay, in order to make sure that you've got the correct value. Does that make sense? So you don't need a memory fence. So that's a classic instance of speculative parallelism. It occurs when a program spawns some parallel work that might not be performed in a serial execution. So you're performing it anticipating that you're probably going to need to do it. Okay, and then typically what you want to do is have some way of backing out if you discover that that you've made it, that you didn't need to do that way. Have some way of making sure that you don't do any more. Okay, so basic rule of thumb of speculation is don't spawn speculative work unless there's little other opportunity for parallelism and there's a good chance it will be needed. So one of the things I've seen in research papers, no less, is people who say, oh, I'm going to, I have a calculation where I'm trying to find, say, the minimum of a bunch of values. And so I'm going to, spawn off, n things, each of which is looking for the minimum. As soon as the minimum one comes back, I'm going to retract all the other computations. And I'm going to get superlinear speed up that way. Because in the serial execution, I might have done the longer one first. And maybe the minimum is not the first one or whatever. And so they claim superlinear speed up by doing speculative parallelism. But that's not really a good example because there was a better serial code. If that was really a good way of doing it, they should have been doing what's called dovetailing, which is doing a little bit of this computation, a little bit of this, a little bit of this, a little bit of this, et cetera, and then going back. That would have been a better algorithm for which you would then use it. And the risk they have is that they're spawning off n things of which most of them may not be needed, and now they don't get any speed up even though they've just used a lot more work. And that often is a bad choice. So usually you don't want to spawn speculative work unless there's little other opportunity and there's a good chance it'll be needed. Okay? My experience is, what kind of chance do you need? You need to, have certainly less than, for parallelism, you got to have, if the chance that you're going to need the work, if you have P processors, if the chance that it could be not needed is less than Actually, I have a theorem at the end, which I'll refer you to, okay? Because it's a little bit hard to say because I didn't put it on the slide. But there's a final slide for this, which gives a nice little theorem about when you should do this. So now let's talk about parallel alpha beta search, because that's kind of what you're doing with your principal variation search. So if you remember the analysis done by Knuth and Morris, they basically showed that for a game tree with branching factor B and depth D, an alpha beta search with moves searched in best first order examines it exactly B to the ceiling of D over 2 plus B to the floor of D over 2 minus 1 nodes at ply D. So that's basically square rooting the amount of work that you would need if you did a full depth ply. That's with alpha beta, okay? So the naive algorithm looks at B to the D nodes at depth D, and so for the same work, the search depth is effectively doubled or the work is square rooted. Okay, so that we saw last time in Helen's lecture. Okay. So the key optimization here is pruning the game tree. And as I mentioned at the beginning of this, when you prune the game tree, you've got what's effectively a serial thing. And if you let something go ahead, you may be working on something that would be pruned. So then how does the parallelism really help you there? You're just wasting processors that could be better spent perhaps elsewhere. Except where else can you spend it? Because there's no other parallelism in the code. So we want to find some solution. So the solution comes from an idea from a very nice paper by Burkhard Monin and some of his students in Germany. And they made the observation that in a best ordered tree, the degree of every node is either 1 or maximal. This is not their observation. This is actually the observation in the Knuth paper, okay? So when you have a best ordered tree, if you can get all the moves ordered in their true order, okay, then it turns out that either you're exploring all the children, or you are refuting something and you get a cutoff from the very first one that you look at, okay? And so in this case, for example, it turns out on the principal variation, those are all full width. Sorry, you have to explore all the children. And then from there on, it alternates. One level, it's you have just a single child that needs to be explored, and when you explore it, if it's best ordered, you will get a beta cutoff for the others. And then it alternates, and then it's full width. And so their idea was to say, well, if the first child fails to generate a beta cutoff, speculate that in fact you have the best one, and the remaining children can be searched in parallel without wasting any work. Okay, so if it fails, you're going to say, oh, I'm going to speculate that this is in fact a full width thing. Now in practice, you don't necessarily get things best ordered, but there are a bunch of heuristics in the code we've given you and in chess code to make it so that you tend to do things in the proper order. The most important of those is, if you've seen the move before, okay, and it's in the transposition table, you use the move that you've seen before even if it's to a shallower depth. Okay, you guess that that's going to be the best move still, even if you search deeper, and that's pretty good. And then so they call that the young siblings weight algorithm. They actually called it the young brothers weight, but in the modern era, we call it young siblings weight, okay? We abort subcomputations that prove to be unnecessary. So you're going to start out searching, but then you want to, get rid of things that you discover, oops, I did get a cutoff from searching from one of these things. I don't need to do this. Let's not have it keep spawning and generating work in some other thing. Let's abort it. And here's the idea for the abort mechanism. So what you do is the abort can occur at any given node, saying I don't need to. You get a beta cutoff. You want to abort all the children that wouldn't have been searched anyway. But they may have already been spawned off. So you have a record in each node that tells you whether or not you've aborted. And what you do is you just simply climb up the tree, okay, to see whether or not, periodically, whether or not you have an ancestor who is aborted. If you have an ancestor that's aborted, says, I'm aborting my the side computations, then you say, oh, I'm done, and I just have to return. Okay, and so you check that on a regular basis, okay? So do people follow what that mechanism is? And so that's basically what you're going to be implementing for, for the parallelization. Okay, is this thing of climbing up. You're going to spawn, you're going to guess after you've searched one child that it's good. Hey, actually, some people say, why don't you check 2 before you, search the others? Okay, so that you're even more sure that you don't have a cutoff because neither of the first 2 aborted. Because in practice, of course, the game tree is not best ordered, and so you're going to waste some work. Okay, so but the idea is you're going to poll up the tree to see whether or not, and of course you don't want to poll on every evaluation that you do. You want to just poll frequently. So you may have a counter in there that says, okay, every 10th time I'm going to poll up the tree, or every, you put a voodoo parameter there that says how often it makes sense to actually check, because there's cost to going up and checking, okay, versus exploring more of the tree, okay? And so I have an example here, and I think this is where I'm going to cut this short. So let me, there's an example which I suggest you take a look at. I want to, as I say, spend time doing Q&A and talking about the other parts of the program and give you folks some good ideas for things. So this is sort of the theory thing, and then I have some slides that will explain this with examples in more depth, because I don't expect that everybody got every detail of this. Okay, so this is so I have some examples and so forth in here that I'm going to let you guys look at on your own, okay? Now, if you parallelize the spawning off loop, okay, of the younger siblings, you will get a code with races, okay? And the reason you'll get races is because there are 3 data structures, okay, that the search is employing that are kind of global. The first is the transposition table, looking things up to see whether or not you've seen them before. That's a major optimization. You don't want to get rid of the transposition table. And so you have a choice with the transposition table. What are you going to do with it? Are you going to lock it so that the races become, at least your data race free and updated atomically? Or you could replicate it. For example, you could have a worker local copy of the data structure, and each worker that is working on it only accesses their own local copies, okay? You can use you can make a copy when things are stolen, or you can make just one where you just maintain it locally. Or you can decide that, well, even if there's a race there, the odds that it's going to affect how I play in the game are not that high, so I'll run with a race, okay? Because any other solution is going to be more expensive, okay? And then maybe you get funny answers. So one thing is for that kind of data structure, let me just recommend is that you have some way of turning off the data structure so that you can actually do the parallel search and get deterministic repeatable results. Okay, so even though it may be aborting, some things may not be aborting, you want to have some way of executing. And so, for example, you want to be able to turn off even the speculation in your code. So you can test all the other things in your code that don't depend on the speculation. Okay, because if you have something that's non-deterministic, as I say, it's a nightmare to debug. Okay, so you're going to do the evaluation function. Hey, turn off, if you're testing it, turn off the speculation. That you should be able to find out whether you've got bugs in your evaluation function. There's no point in discovering you have a bug and it's like, well, where did it come from or whatever. Okay, so you want to have things turning off, and also you want to have ways of turning off, for example, access to the transposition table. Yes, I'm going to speculate, but no, I'm not going to access the transposition table in parallel because I may get a race on the entry in the transposition table. Okay, the hint that I will give you for that is that in the code that for our program that took second prize in the World Computer Chess Championship many years ago. I think it was in 1999, where we actually almost won the tournament, and we lost in the playoff. We would have won the tournament, except that our programmer suggested a rule change at the beginning of the tournament that everybody agreed to, and then we were on the short end of that. Otherwise, we would have been world champions. And that was the last competition against computers that Deep Blue, the IBM computer that beat Kasparov, the human challenge, just a few months later. They performed it, and they placed third in the tournament. We tied for first. Our only loss was to Deep Blue. Okay, and we were running on an 1824 node supercomputer at Sandia National Labs, a computer that probably is today less powerful than this. Okay, so but it was very big type of computation. So we were. They basically said if there's a tie, they're going to base who wins on strength of opponents. So you take a look at your opponent's records, and if you had stronger opponents, you'll win against somebody. And we said, if there's a tie just between two programs, we should really have them, face off against each other as an extra round. And everybody said, yeah, that's a good idea. And then wouldn't you know, at the end, we had the strongest opponents, and we were tied with another program called Fritz, an excellent program. And we were out-searching Fritz in the playoff game, and then we saw a move that afterwards, when we were able to do offline searches deeper, we were out-searching them by like 2 ply. Okay, but then there's a move that looks like it's a good move for the depth we were looking at it. Doesn't look like a good move if you search much deeper, or frankly, if you search much shallower. Is one of these things where it just looked like a good move for the ply we happen to be searching. Because there's no guarantee, because you can't see the end of the game, there's no guarantee that if you search deeper, you're actually going to beat somebody else. Okay, sometimes because there's the horizon effect of you simply can't see what's coming up in the future. You can only see sort of on average. So we made this bad move. We almost recovered. We almost tied. Had we tied, we would have been world champions because we won the tiebreaker. And we weren't able to recover from the error. And so we took second prize. It's like, Anyway, in that program, we decided that we were just going to let there be a race. And on the transposition table. And the reason was we calculated what are the odds that the race actually affects the value that you would actually pick that value. And if it affected the value, what are the odds that it affects the move that you're going to make? And if it affects the move you're going to make, what are the odds that it affects the game? And if it affects the game, what are the odds that affects your result in the tournament? And when you figured all these things out, it was like, we would slow the program down more by putting in, for example, locking, okay, because that would slow down every access than we would if we just ran thing. Because one of the things that happens in alpha beta, that thing is if you get an extreme value, usually those are lopped off. Because if it's such a good move for you, your opponent's not going to let you play it. So if you ended up with a score that was extreme because it was based on a value that you were racing on, usually it's going to not even propagate up to the root of the tree. So anyway, so we just ran, naked, so to speak. There are two other data structures you're going to have to worry about to make decision about. Another one is the killer data structure. So the killer data structure is a heuristic that says, at a given depth of code, you tend to see the same moves that are good. And a move that is good for one thing at a given depth tends to be good for something else. So for example, it may be that you play bishop takes queen. Okay, so you've won the other player's queen. And then their response is to do something irrelevant. Okay, well now you made them. Okay, well, there's a lot of other moves where you could mate them on that move, okay, for which they're playing things on the board that are irrelevant, okay? And so the same type of move tends to be a killer. Always you're able to, at that depth in that position, you're able to make the same move, and if they don't address the issue, that's always a good move to check. And so that ends up being ordered near the front. So the killer table keeps track of that. And I think in our code we have 2 killers. Is that right, Helen? I think it's set up to allow you to do up to 4 killers, but we only do 2 in the code that we gave you. I mean, you can enable it and see whether 4 killers. But that's a shared data structure. And so one of the questions is, should you be keeping a local copy of that, or should you be, using a global one that they all share? Okay, and updating it. The third one is the best move table, which is used to order all of the low order things. So the first thing that's most important is, did you get a move out of the transposition table? That tends to be quite accurate. Then the second is, did you get a move out of the killer table? And finally, it's sort of like, statistically, how good are these moves? Have you seen these a lot before? And if you've seen them a lot before, that's how the other moves get ordered. And that's kept in the best move table. And once again, that's a shared table. In the search, you're going to have to figure out, do you want to do a thread local, worker local copy, or do you want to synchronize it, or how are you going to manage that data structure? Okay? And the answer, I would say, is different compared to what you do with a transposition table. Okay, transposition table, generally, it's not worth locking or whatever. And it is good to share, because if you have seen that move before, that saved you a huge amount of computation to be able to look it up and not do it. Okay, so those are some of the tips for parallelization, which you'll get to in the beta 2. But now I want to talk about, for most of the rest of the time, talk about some of the other things that you can do with the code you've currently got. Let me take these in some order, and then we can ask questions. So opening, who's contemplating doing an opening book? Anybody? For beta 1? Are you going to do an opening book for beta 1 or beta 2? Who for beta 1, let me see. Okay. Beta 2? Who wants to do an opening book for beta for the final? Okay. Yeah, okay. So, the idea here is to pre-compute best moves at the beginning of the game. So that, it's like, well, we know what the starting position is. So why don't I, spend $1,000 or whatever on Amazon and compute things to some ungodly ply, right? And see what the best moves are at the beginning of the game and put that into a book so I don't have to search those. So that's the idea. I think to begin with, there are lower hanging fruit than the opening book. If you look at it, you're going to be in opening book, if you're lucky, for 6 or 8 moves. And the games tend to last. Have you looked to see how long games tend to last? Yeah. What is it? No, most games don't go 4,096. We don't let them go that long anyway. So anybody take a look statistically to see how long games are? I think they tend to be like 40 or 50 moves. Okay? I mean, this year is different from other years because we have different rules, but I think it's like 40 or 50 moves. So you're not spending, so you're doing something that will help you in 10% of the game. Whereas there are other places you could do it which is going to help you in the whole game. Nevertheless, we've had teams that did a great job on opening books and clobbered people by having a fantastic opening book, okay? It's actually cheaper to keep separate opening books for each side than to keep one opening book for both sides, okay? And in this game, it's actually fairly easy to keep a symmetry thing and basically have one opening book that works for the side on move, okay? And that allows you to store. You don't have to store, if I make a given move, if I have a given position, I only need in principle to store one answer for that position, okay? Whereas then my opponent may make any number of moves, for which then I only need to know one move, what's my best move in that position. So you can see that you're only having to, you have, once again, this property that on my move, I only need to have one move stored. My opponent's moves, I need to have all the moves stored. Okay, and then my move, I have one move stored. And that basically means that you're effectively going twice the depth as if you kept all my moves and then all of the other opponent's moves and then all of those. Because when I do that, it's like, well, why do I need to know what the best move? So it's better to keep them separate. When you build the opening book, you'll store a lot less. You have a lot smaller storage. You'll be able to store a lot more moves if you do that. Okay? But I would say not necessarily the first thing I would go to optimize. But it's also the case that this is a place where one of the teams built a fabulous opening book one year, and one of the things about the opening book is it allows you also to sort of threshold and say, in a given move, I don't just have to have one move. Let me have three moves, and pick randomly among them so that I'm not predictable. What the team did that used the opening book is they observed that everybody was just searching from the beginning, so they were all finding exactly the same moves at the beginning of the game. And so they knew exactly what the path was that all the other programs were going to follow. And so they could make the best move on their move. But if you have something that's got some randomness to it, and there is a jitter in there, who found the randomness, the place we insert randomness in the code, right? So there was, I think Zach had a comment on Piazza about that. So there's a place in the code where we dither the amount so that you will get unpredictable results. And that way you won't always play the same move, okay? Just by changing things. It's like, a tenth, a hundredth of a pawn value is like not very big. And like, who cares whether or not, we have, we're not actually, these heuristics aren't measuring things so closely that we care about a hundredth of a pawn. So you can dither things and have one move be better than another and not really affect the quality of the playing, okay? So it is a good idea to do something to not be so predictable, okay? But to build a full opening book, that's a lot of work for beta 1, okay? For beta 2 and the final, yeah, you'll get to that point. The next thing is iterative deepening. Do people understand how this part of the search code works? Yeah, no? Let me go over it, okay? So you can imagine saying I'm going to search to depth D. And in fact, instead of just searching depth D, we do a depth 1 search. If you look at the code there, if there's a depth 1 search, then we do a depth 2 search, then we do a depth 3 search, then we do a depth 4 search, and we keep doing that until our time control expires. Why is that a good strategy generally? Well, First of all, the amount of work with each depth is growing exponentially. So you're only spending, in principle, a constant factor more work than you would if you searched to depth D right off the bat, okay? But the important thing is that you can keep move ordering information as you search deeper. And the move ordering information, remember, we want our searches to use best first move ordering so that we get all the cutoffs we can possibly get, okay, for pruning. And so by searching it easier, actually you end up with better move ordering, okay, because when you find the same position in the transposition table, you say, oh, well, I didn't search it as deep as I need to search it now, so I can't use the value that's in the transposition table for the position, because it may be, say, I've searched something that's, ply 8 in the transposition table, but I've got to search to ply 9, not good enough a search. But the value, the move that you found at ply 8, that's probably a pretty good first move. Pretty good best move, guess at best move. Okay? So by doing iterative deepening, you actually get the move ordering for all those intermediate positions, really, really, really strongly, because that transposition table is the very best information you've got for what the first move is, what your best move is, sorry. Okay? And also, as I mentioned, it's a good mechanism for time control. Is that clear? So that's why you bother. It's one of these things that looks like it's redundant. Why are you searching? If you're going to search to depth D, why search to depth D minus 1? You're going to do that as part of depth D. Well, no, because you're going to get move ordering information that's going to be really valuable when you search to depth D minus 1, so that when you search to depth D, you've got much better pruning than if you just went straight to depth D and had no information about the move ordering. Does that make sense? Endgame database. So here's the idea. If there's a few enough pieces on the board, you can pre-compute the outcomes and store them in a database. Okay? So for example, the most common database to come up with is the king versus king database. Okay? So if you do king versus king, that means that it's not that you expect the game will end up as king versus king. It's that you're going to encounter that in the search. It'd be nice to know who has the win if you're king versus king. Now, the code actually plays optimally for king versus king. Okay, the code we gave you will play the king versus king, perfectly well. And in fact, there's just two heuristics that are responsible for that. One is what is called K-aggressive heuristic, and the other one is, which basically makes you move towards your opponent, and the other one is the K-face heuristic, which makes you point towards your opponent. And those two things turn out to do a pretty good job of when there's two kings in playing, they go through this little endgame. Did everybody do that by hand, by the way? Did you play king versus king? So really good idea if you want to understand the game is just go and do a king versus king version of the game. Get an 8x8 chessboard and just put down two tokens that you call are kings that have orientations, and then just the two you and a friend just try to see if one can mate the other. And you'll see that it goes through a very ritualistic type of behavior, which ends up with one of the kings being mated. So it's nice to know which one it's going to be, so if you encounter that. But here's the question is, how many games actually make it to an endgame? Once again, you have to look at what the odds are there. Because if games are ending in the middle game, there may not be any need to search all the way to the end game. Okay, so that's something that you need to weigh. Okay? Now, if you do an endgame database, it doesn't suffice to just store win, loss, or draw for a position. And the reason is because you can get into a situation where you've got a winning position, and then you say, okay, well, let me move to another winning position, and another winning position, and another winning position. Oh, and I'm back at my original winning position. And I just keep going around in a circle, always in a winning position, never moving towards the win. Okay, and that, of course, will end up in a draw. So you need to know which direction do you go for the winning position. So the typical thing you do there is you keep the distance to mate to avoid cycling. So you go from, instead of keeping just a Boolean value, you say, here's my distance to winning. Okay, my distance to winning is 6. Now when I'm searching, I don't want to go a distance to winning that's 7 or 6. I want to go to a distance to winning that's 5 when I make my move. Okay, so it's very important to make sure that you maintain the distance in order to avoid cycling. Quiescent search, we talk about quiescence, which is, to make sure that when you're doing the evaluation, you're not in the middle of an exchange. So you zap their pawn, they're going to zap your pawn, or maybe even zap your king. Okay, and you don't want to evaluate in the middle there. And so the idea of quiescence is that when you're done with the regular search, you just play off moves that involve captures. And then you evaluate the position. Okay? So that's quieting the position. Okay, make sense? Another heuristic there is null move pruning. In most positions, there's always something better to do than nothing. So sitting still is usually not as good as actually making a move, okay? And so the idea is, suppose that I can forfeit my move and search a shallower depth, and I still have the best position, okay? Then I still am winning. Well then, and it generates a cutoff, then why bother exploring any other moves? I probably am in a really good position here. Okay, and if I don't manage to get a cutoff from the null move, then I then I do the full depth search. Okay, so the place this is dangerous is in Zugzwang in chess. It's called Zugzwang situations. So Zugzwang is a situation where everything is fine, but if you have to make a move, you lose. So usually having the advantage of a move, that's called the initiative in chess, and that's a good thing. You want the initiative. You want to have the extra move over your opponent. But there's some situations where if you move, you lose. Okay, and so you want to make sure you don't have a Zugzwang situation. I don't actually know if there's a Zugzwang situation in Leiserchess. Okay, so if somebody comes up with one, I'd be interested to see that. Where if I had to move, I lose, but if I sit there. So in chess, what they do is in the endgame, that's when Zugzwangs come up, they turn off the null move pruning. So is this clear what null move does for you, what's going on there? So I see some people who are quizzical. Anybody want to ask a question? I see some people with sort of quizzical looks on their faces. Okay. So the idea is for a null move is my position is so good, okay, that even if I do nothing, I still win. Okay? So I don't want to search anymore in this part of it because I get a beta cutoff. You're not going to let me make this move, the move that got me here. Yeah, question. Oh, did you? Yeah.
No, that was it.
Okay, that was it. Okay, good. Yeah. My move is so good, I can do nothing and I still win. Okay? And so why bother, let me verify that without necessarily doing as deep a search. So null move is fairly cheap to do, and it often results in in a lot of positions for cutoff. And if I don't get a cutoff, then I just do the normal search. Okay, this is a pretty complicated piece of code, isn't it? Okay, pretty complicated. Okay, there are other situations. We mentioned killers. Okay, there's also move extensions. So typical move extensions that people look at is you grant an extra ply in chess if the king is in check, or for certain captures, or if you have a forced move. So suppose you have a move and it's the only move you can make. Then don't count that as a ply. So you can search deeper along lines where there are forced moves. That's what they do in chess. In Leiserchess, not quite so clear what you do. Okay, which ones you would do extensions for. Okay, because it's rare that you have just one move. in Leiserchess compared to in chess, where you have by forced move, it's like if you don't do this, you're going to get captured or, mated or what have you. Okay, so that may come up in Leiserchess, but anyway, it's something to think about. So the transposition table, so we talk about this as a search tree, but it's really a DAG because I can get to the same position by transposing moves. This guy does A, this guy does B, this guy does C, this guy does D. I may get it to the same thing by doing, A, D, C, B. I transpose those two moves, and I get to exactly the same position. Okay, and so I'd like not to search that position again if I've seen it. And that's what the transposition does. There's a quality score that is in the transposition table that tells you how good a move you've made, and the quality is essentially the depth that you had to search in order to establish the value that's stored in the transposition table. And so you don't want to use something of too low quality when you're searching. If you have to search to depth D, something of quality D-1 is not good enough. Okay, because otherwise you'll not be searching, the full tree. But something typically that is deeper, if I'm looking at depth D and I find something in the transposition table that's D+1 or D+2, that's great to use. That just gave me an even deeper view of what's behind that move. Okay, and so if you look at the logic there, you'll see that that's how they do it. It's very tricky. One of the things that's tricky is when you find a mate, how you store that in the transposition table. And you'll see there's special code for handling mate positions. And the reason is because what you're interested in doing when you find a mate is knowing your distance to mate, but not from that position, the distance to mate from the root of your search. Okay, so for example, let's say this is the root of my search, and I search down to a given point. And now I do a lookup in the transposition table, and I discover that there's a mate in 5 here, okay? And this is, let's say I've searched 9-ply or something, okay? Well, if I store that this is a mate in 5, and I store the value for mate in 5, then if it makes it up to the top here, it thinks there's a mate in 5. But there isn't a mate in 5. There's a mate in 14. Okay? So when you look it up and you discover there's a mate in 5 in the table, you have to do a little bit of a calculation to translate that into being a mate in 14 as the value that's going to be used here rather than a mate in 5. Does that make sense? So you'll see that's the logic that's in there for dealing with mates. So a mate basically takes a very large number, way larger than all the material on the board, and then it subtracts what your number of ply is to get to mate. So it's some big number, I don't know, 32,000 or something, minus the depth to mate is how you represent a mate. So it's some very, very big number, and then minus the depth, and that way you can make sure that you're going for a mate in 13 instead of a mate in 14, for example. Preferring that you take the shorter path. Make sense? So that's one of the things to look out in there, and there's also a lot of stuff in there. The transposition table has, we talked about caching. It's actually a k-associative cache, k-way associative cache. And so you can vary k to see what's the best choice of, how many entries you should have. The more entries you have, the longer it'll take you to search them. On the other hand, the more likely it is that good moves stay in the cache. Okay, so you can decide what's the right trade-off there. Okay, so there's a good tuning optimization there. Okay, questions? Any questions about transposition table? Transposition table is a major optimization. So Zobrist hashing. So most of these Helen talked about at some level, but I wanted to sort of give a chance to have people ask questions. Nobody's asking questions. Came here for Q&A. All you're getting is A. Okay. Let me explain Zobrist hashing again a little bit, okay? So Zobrist hashing, very clever idea. So we have our board, right, with a bunch of pieces on it. That's probably the wrong number of squares, right? That's 7 by 6. Okay, who cares? Okay. So the idea is that what I'm going to do is have a table of random numbers that I'm going to compute in advance. And this is going to be indexed by, my row, my column, my piece type, and my orientation. Okay? And every different combination of row, column, type, and orientation corresponds to a different random number in the table. Okay? So we have some sort of random number there. Okay? So, and what my hash function is it's the XOR of all of the values of all the pieces that are on this table with their orientations. Okay, so if I have a king here, that's a white king, I guess I need to know who's not just what the type is, I also need to know whether it's white or black, right? So the side. Okay, I think actually that gets encoded somehow, but in any case, I think maybe in the type we actually keep whether it's a white or pawn, black pawn. Yeah, it's in the type, I think, is the way we actually implemented that. Okay, so there's white king, black king, white pawn, black pawn, or space. So if I have a king there, that corresponds to a certain value. If I end up with a pawn here, let's say a white pawn, then that will be another one, and I XOR those together. And I take the black king, okay, and I XOR his position is, and the black pawn, XOR that in. And so I XOR all these 4 values. That's the hash function that I use to do things like look up things in the transposition table. Now, if I had to compute this every time I change the position, that's if I have a lot of pieces, how many pieces I've got? I've got 7, 8, 16 pieces, right? Each side has 7 pawns and a king. So 16 pieces, I have to do 16 XORs in order to compute my hash function. So Zobrist hashing is really a lot clever. It takes advantage of that XOR trick that I taught you in the first, no, it wasn't the first, it was in was the second lecture? Yeah. The bit tricks lecture, okay? And that is that XOR is its own inverse. So if I want to remove a piece, let's say I'm going to move this pawn, okay, from here to here. So I remove this piece. What do I do to my hash function to remove a piece? I look up the value for that pawn in the hash table, and I XOR that into my hash for the table, and I now have a hash for those 3 pieces left. Does that make sense? So I have my hash function, which is a hash of the 4 things. I'm not sure you guys can see very well over there, and I basically simply XOR it with the hash of, the pawn that I removed, of the pawn that I removed in this case. And now I moved it to here. So what do? I look up that one, and I XOR that value in here for the new position, the new pawn position, and that gives me now the hash for the new table with the pawn in that position. So any move that I make, I can basically update my hash function with only 2 XORs. And XORs are very fast. They're one instruction. They're one, and they can do lots of XORs and stuff. So this is actually a very, very cheap thing to do. Okay, very cheap thing to do. So that's Zobrist hashing, that you can keep these things up to date. And that's something we implemented for you. That's an optimization that was a freebie. We could have given you the hash function, like this and had you implement that, but this is one of the ones we gave you as a freebie for optimization. You're not all saying thank you very much, Professor Leiserson? Okay. No, in some sense, I took away an opportunity for optimization, didn't I, there? Okay. And so in the transposition table, there are records for the Zobrist key, the score, the move, the quality, also a bound type, whether it's upper, lower, or exact, because when I return something from alpha beta, I only know a bound on it if it's greater than alpha or less than beta. And in some sense, the age of how old is this move, because as things get older, I also want to age them out of the table. There's several aging things there, and you'll see the best move table also has an aging process, whereas every time it updates the values, gives a new value, it ages all the other values so that they gradually disappear and aren't relevant. One of the ones that people have get confused about is the late move reductions, so-called LMR. Okay, this is the situation where I'm going to do, let's say, my parallel search to, of all my moves. And the question is, once again, you're trying to prune everything you can, okay? And so the idea is, which are the moves that are more important to search deeper? The ones near the beginning of your move list, if it's sorted in best first order, or the ones towards the end of your move list? So where is it most important to search deeply? For things that you think are possibly the best move, or the ones that you think are the worst moves? Yeah. Yeah, it makes sense to search the best moves, right? So the idea is, well, if something is way down on the move ordering list, why search it as deeply? It's probably not as good a move. And so let me search it more shallowly. I probably don't lose much of an opportunity to discover that that's actually is indeed a bad move. Okay, there's a reason it got ordered down there. And so that's late move reduction. With a good move ordering, a beta cutoff will either occur right away or not at all. So you search the first few moves normally, and then you start reducing the depth for moves. I believe in our code we have two numbers where we reduce by depth 1 after a certain number of moves and reduce by depth 2 after a certain number of other moves. Those are things that you can tune. I wouldn't tune them very much, I don't think, just because, and once again, I could probably be wrong here and some of us discover, if you tune it like this, it's way better, okay? But that's the idea of the late move reductions. Probably one of the most important things to think about is the move, is the representation of the board. Right now, we represent the board as it is, okay? That's a terrible representation. It's very, time-consuming. There's sort of two major ways you can do it. I didn't put the other one here. Okay, well, anyway, so one of them is bit boards. Here you use a 64-bit to represent, for example, where all the pawns are on the 64 squares of the board. Okay? And then you can use pop count and other bit tricks to do move generation and to implement other chess concepts. Okay, so if you're looking to see what are the possible places a pawn can move, and you want to say, can they move right? And let's say it's stored in row major order, you can just do a right shift by 1, and that tells you where are all the places that those pawns could move, and now you can just pick them off one bit at a time to generate your move list, okay? And then you can do it that way. If you're going to move up a thing, well, then you're actually doing a shift by, or down, you're doing a shift by how much? By 8. Right? To move up or down. Okay, if you're storing things in row major. Right? That makes sense, right? So if it's 8 by 8, and you're keeping a bit for each thing, then if I want to generate, where is this one? If I shift this whole thing stored in row major order by 8, if I shift it right, it basically puts it there. Okay? So moving it by, 7, 8, and 9, that gives you, and then shifting it by 1 gives you, or -1 gives you this, or left by 1, and then similarly you can do by, shifting by 7, 8, or 9 that way, and I can generate all the possible moves. So that's one way of doing move generation, is using bitboard. And there are a lot of things, for example, that you can do with bitboards in parallel, because you can say, did I make a capture here? Okay, or let me use a bitboard to represent where the laser goes. Did I make a move that is going to affect the path of the laser? Okay, because one of the major optimizations you can do is in the evaluations in dealing with the laser. Okay, because you're spending a lot of time stroking out laser positions. What's the point of doing that? If you made a move of something and it didn't affect where the laser goes, why bother, doing it out? You can just cache what the value of the laser is. And there are a lot more good stuff on the chess programming wiki. Okay, so yeah, question.
Manage a right shift when onto the edge of the board. With the shift by 8, it's clear when it falls off the board.
Yeah, you got to be careful there, right? Because if I do a shift to the right, for example, so what will I do? I'll just do a mask to eliminate all the things that got wrapped around. Okay, right? So 2 instructions or whatever. Yeah. Details, yes. Details are good, though. Good question. Good question. Who's timed their program? Where are the opportunities that you see for performance engineering for a first pass? What are the expensive things? What do you have as expensive thing? Sorry, the marking the laser path. Yep. Good. What else is time expensive?
Laser coverage, accuracy path.
Yeah, laser coverage. Boy, that is really expensive. Okay, that is really expensive. So where else is expensive? What else is expensive? So I would definitely go after, L cover. That's a huge one to go after. One of the things, by the way, if you are making your changes to the code, and you're going to change the representation, leave the old representation there. Take it out at the end. Add the new representation and put in assertions that say that things are equivalent or whatever. But don't get rid of the old stuff, because you'll end up with broken code. And definitely use things like perf t to tell you whether or not you made any changes if you touch anything with move ordering. Sorry, not move generation, not move ordering, move generation. So where else is expensive? Yeah.
Can you explain the laser coverage first?
Sure. Do you want how much detail do you want? How it actually works?
What's it supposed to do?
Okay. So what it's supposed to do is figure out how safe. The idea is, I want my laser to get closer to your king, and I want your laser not to be close to my king, right? And if I can move into positions where my laser is closer to your king, but your laser doesn't get closer to my king, that's a good sort of thing. But when we say get the laser close, what happens when I've got, say, let me do it this way. A position like this. So here's the, okay. Suppose I look at this position. How close does the laser get? Let's say I'm black here, and I look at the laser. Well, the path of the laser is it bounces there and goes across, right? Okay. So I didn't get very close to the king there. But I'm one move away from getting it pretty close. Because if I just move this guy out of the way, now I've got it really quite close. Okay? So if I compare that to, let's say, a situation where instead of the pawns are there, let's say a pawn is here. Okay? Now, the laser is actually closer to the king than it was in the first position, but it's a much worse position, right? The first one was much better when I had the pawns here and here, because I was simply one move away from getting it really close. And so if you use just the direct laser thing, and we did some tests on this, this turns out to be not very, it doesn't guide the program very well on getting into situations where my laser is getting close to your king. Does that make sense? So then we said, well, how can we, how should we measure how close the laser gets? So what we said is, well, let's take a look at all the possible moves from here, of one move, and then look to see how close we get things. And the way we did that is we said, let's, this took, actually Helen and I worked on this really hard, okay? Because this is a new heuristic that we have not used in previous years. And it works great, it's just slow as anything, okay? But it works well. So you have to evaluate, is it worth doing something if it's really slow? It may be that you do better to use a simpler heuristic and get deeper search than it is spending a lot of time evaluating. But anyway, we gave you one that if you can make it go fast should be really good. So what the idea is that what we do is we look at all the different paths from moving any piece, one piece, and look at the paths of the laser. And what we do is we count one for every position that we go away, 2, 3, 4, 5, 6, 7, etc. We actually add an extra value if we bounce off an opponent's. How much do we add, Helen? Do we add 1 or 2 if we bounce off an opponent? I think 2, yeah. So if this is an opponent's pawn, we would basically go from 3 to 5, 6, 7, 8, 9. And we basically do that for all the moves, and the way we combine them is we take the minimum number that I can get there. Okay, what's the cheapest way I can get to every square that the laser goes? So we take all the different moves, we stroke them out, and we take the minimum. So if I have another path, let's say by turning the king, it will go this way, and there's another one here that's my pawn. Okay, then I may get there in 1, 2, 3, 4, 5, 6, 7, and so then this would become a value of 7 here. Okay, so that's the first thing, is we basically get a map of, how close are things. And the second thing we do is say, well, how valuable is it to have these to be near the particular king? And what we ended up with is something where if I look at the distance that I am away, let's say this one, for example, is 1 row and 1 column away. This is 0 rows, 0 columns. We use, I think it's 1 over the row plus 1 times 1 over the column plus 1, okay, as a multiplier to weight how good it is that we've been close to the king. And we invert these values so that they're, so that the closer you, so that it's better to have a smaller number there, and then we add them up. Okay, and that's basically gives, don't quite add them up. We actually, no, I'm sorry. What we do is we look at these things as a fraction of my shortest path distance. Sorry, that's what we did. Yes, I'm sorry. That was a previous heuristic. So here, for example, let's say this is the 9. The shortest way of getting there is 1, 2, 3, 4, 5, 6, 7, 8. So this would actually, when we do the conversion, we'd give a value of 8/9 for being in that square. Okay, so we didn't get it. Whereas this one, the shortest path distance is 7 because of this path, and you can get there in 7. This would have a value of 1. So this is better, And so we do that for all the squares. So we get a fraction of how much do we do, and then we weight it by something like this, which falls away quickly. But it's important in heuristics like this to have a smooth path so that you can get things closer. If I made all these things be 0, it wouldn't know that it could, move up and get a little bit better, in the second or third order, digit to get closer. And so then we add it all up, and that ends up being a number we discovered that's sort of in the range of, what did we figure the range was there? it was like, up to like 4 or so, right? Something like 4 on average, would be the maximum value it'd be. And then we said, okay, then we have this magic constant multiplier that you can play with that says, okay, let's represent that as a fraction of a pawn. How much is that worth? And we multiply by that value. Okay? So that's what we're doing. Okay? So that it makes it so that we do tend to move our laser closer. We subtract how close the opponent can get from us, and then we say that's the evaluation. Now, if you have a better way of determining whether a laser is getting close than this one that's cheaper to compute, that's good. Okay? For first pass, I would just simply try to make this go fast. Because for many of the moves that you're going to look at, it's going to be moving this pawn, to there. Nothing changed. There's no point in stroking this out and calculating the minimum, etc. Because it didn't touch the laser path. Things that are going to touch a laser path are things that you move on or off the path. So why bother? Okay, and so if there's a clever way of hashing this, so that you, or caching it, so that you can, do things, that's good too. Okay. Any questions about other things that could be done? So another place I'll tell you that's a good idea to look at is, especially once you get this heuristic to operate a little bit faster, is the sorting of moves. Okay, is actually pretty expensive. Okay, what's the, once you figure out here are all the moves, there are a lot of moves, now you go through and you do a sort. And if you think about it, in a best move order tree, sometimes you only explore one of those. So why'd you bother sorting all of them? Okay? On the other hand, sometimes you do need to sort all of them. So how you optimize that sort so that you don't waste time sorting stuff that you're not going to actually ever explore, that's another opportunity for optimization. Okay? Yeah, question?
What do you sort the moves by exactly?
The moves are sorted by these things like there's a sort key in there that represents a whole bunch of things, like whether it was a killer. If it's a killer or it's a transposition table value, it gets a very big value. If it's a statistical thing that the history table says, historically this has been a pretty good move, then you get another value. And then exchanges get ordered and so forth. So there's a bunch of things that are, where you end up with information and then it sorts those things. Okay? So that's actually kind of complicated logic in terms of what the actual values are that are used there. But the idea is, here are all the moves, now let's figure out what's our best guess as to what they are. Most of the good moves are coming out of the transposition table, right? But sometimes the transposition table, it says it's not a very good move, and there may be a better move. Okay, so the quality of what you get out of transposition table is good, but that doesn't mean, that that's always the best move. Okay? Yeah, any other questions about what should be worked on? Let me just make sure Okay, go ahead.
Where does that sorting happen? I've never seen this.
Where does the sorting happen? That happens at the, I think at the move generation. Is that where it is? Is the sort in the move generation? Or is it in search? I think it's in search. I think you're right. Search calls move generation and then sorts it. Okay, I think that's right. Yeah, question?
So one of the things we did before even profiling, which I don't know if good idea or bad idea, we have a very tiny board representation.
A very tiny board implementation?
Yeah, board representation. You can do a lot of metrics on it as well, but it's like very tedious to replace it everywhere.
Yes.
So what's a good strategy?
Well, as I say, keep the old one around.
You still use them.
Well, you use the old one while you're still getting the new one right. Okay? It's also good to be able to go from old representation to new representation and having conversion functions. Okay? But yeah, making representation changes, painful. Painful, and is probably, boy, if there was one tool I would love that would automate stuff like that, that would be it, to be able to change representations of things and still have things go well. I should have mentioned, by the way, the other representation besides bitboard. Another one is just to keep a list of the pieces and their positions. Okay? Because that's going to be smaller than keeping this great big board. Okay, now do you keep this list sorted or do you not keep it sorted? And do you, but the advantage of that is, particularly as the game goes on, that list gets shorter and shorter. Okay, and so you're, if you're doing less in manipulating the board position, that's generally a good thing.
So for the board representation, my recommendation is to refactor all the board axes into a function, and then you would still use the old representation in the function. Then you can validate that you refactored everything correctly, and then you can easily change the board representation to whatever you want and keep changing it without having to do a lot of refactor after that. So find all the board axes and refactor that to a function call before you modify it.
Yeah, because the compiler will inline that stuff. So putting it in a function call is not necessarily a bad idea. And if it doesn't, you can put it in a macro, and it'll be effectively the same thing. So great idea. Great idea. Okay? Yeah, question.
Anything else that wasn't there that you would highly recommend for us to look at?
Testing. If you can test and know that when you make a change it's correct, and that you're not, that's probably the number one hole that people go into, is they don't test adequately. So having good test infrastructure, is good. Yeah?
Some question about node counts. I saw in the Piazza there was some, if you made a change, the node count would stay the same.
As long as you're doing it deterministically, yes.
Yeah, but even the reference implementation is non-deterministic serially for node count.
That's because there's a randomness thing. You turn off there's a little variable, and you can set the variable to be not random, and then it will be.
Like part of the set option RNG.
Yes.
When that's set, it's still non-deterministic.
It's run serially?
Yeah. I checked with, I don't know if is there anything else that should be done, or should it just be that seed option?
I think that's. Andreas, can you give her the mic?
Yeah, did you try the things that I think did for the
Yeah. I got out of the opening book and I set the RNG option.
Okay, let me test it again. So when I tested it, it forced it, so I didn't make it.
Okay.
Yeah, it shouldn't be, if you run serially, the only things that, should be doing things is if you're doing, it should be deterministic if you turn off the random number generator. So as I say, that's put in so that it will behave, non-predictably, but that's exactly the kind of thing you want to find right at the beginning. So that's exactly the thing, is find out all the ways of making it deterministic, and that'll be really important for beta 2. Okay, so Thursday, we have, John Bentley, Legend of the Field, opportunity to meet a celebrity, bring friends, he's going to give a great lecture.